Substitution method. Sometimes we can solve a constraint maximization problem by substituting the constraint into the objective so that the problem becomes an unconstrained problem. We can rewrite the constraint as x sub 1 equals r of x sub 2 and z because the solution for x sub 1 as a function of x sub 2 contains the information in the constraint. We can substitute it into our objective function and rewrite the problem as an unconstrained maximum. Max x sub 2 of g of two elements, the first element r of x sub 2 and z, and the second element x sub 2. Because we wrote x sub 1 as a function of x sub 2, the unconstrained maximization problem has only one choice variable, x sub 2. As with any unconstrained maximum problem, we use the first order condition, partial derivative of g of two elements r of x sub 2 and z, and second element x sub 2 with respect to x sub 1, multiplied by the partial derivative of r of x sub 2 and z with respect to x sub 2, plus the partial derivative of g of r of x sub 2 and z. And the second element of the partial derivative of g is x sub 2 with respect to x sub 2 equals 0. Equation capital A dot 9. To find the critical value of the choice variable x sub 2, we solve the first order equation capital A dot 9 for x sub 2 star. Substitute the solution for x sub 2 into x sub 1 equals r of x sub 2 and z to obtain x sub 1 star equals r of x sub 2 star and z, and then substitute x sub 1 star and x sub 2 star into the objective function to determine the maximum. The following example illustrates this approach, where the objective function is g of x sub 1 and x sub 2 equals x sub 1 times x sub 2, and the constraint is z minus h of x sub 1 and x sub 2 equals z minus x sub 1 minus x sub 2. So the constrained maximization problem is max x sub 1 x sub 2 of natural log of x sub 1 times x sub 2 subject to z minus x sub 1 minus x sub 2 equals 0, equation capital A dot 10. Using the constraint to solve for x sub 1 in terms of x sub 2, we find that x sub 1 equals r of x sub 2 and z equals z minus x sub 2. Substituting this function into the objective function, we obtain the corresponding unconstrained maximization problem. Max x sub 2 of the natural log of open parentheses z minus x sub 2 close parentheses times x sub 2 equals the natural log of z minus x sub 2 plus the natural log of x sub 2. Because the first order condition is negative 1 over open parentheses z minus x sub 2 close parentheses plus 1 over x sub 2 equals 0, the solution of the first order condition is x sub 2 star equals 0.5 z. Substituting this expression into the formula for x sub 1, we find that x sub 1 star equals z minus 0.5 z equals 0.5 z. Evaluating the objective function and the maximizing values x sub 1 star and x sub 2 star, we find that g of x sub 1 star and x sub 2 star equals the natural log of 0.25 z squared. The problem with using this method is that writing x sub 1 as a function of x sub 2 and z may be very difficult. If we have many constraints, this approach will usually be infeasible or impractical.